Okay, welcome everyone to our first CDAC webinar of the year. Today, we're delighted that our colleague Rick Kraus stepped up to give us a very timely talk about measurements of the melting curve of iron at super Earth core conditions, a paper that was just published in Science 2 weeks ago. As many of you know, Rick is a member of the research staff at Livermore. A little bit about his background. He was trained in physics, including geophysics and planetary physics, with a BA from the University of Nevada, Reno, an MPhil from the University of Cambridge, and master's and PhD from Harvard, where he worked with Sarah Stewart on planetary impact phenomena. Rick joined the high energy density physics group at Livermore in 2013 as a Lawrence Fellow, and subsequently joined the staff. Since then, Rick has been involved with, and in fact has led, a number of experiments involving shock and shockless compression, equations of state and viscosity and strength studies to very high pressures and temperatures, experiments conducted at the National Condition Facility at Livermore, as well as at the Z machine at Sandia, and using other platforms. Some 7 years ago, Rick approached me with the idea of measuring the melting curve of iron and structure of iron to terapascal pressures corresponding to super Earth cores. And the NIF discovery science proposal that we wrote with a large number of people listed here. And after many laser shots over the years, he's pulled this all together in a paper that was just published. So it was a long time coming. Rick, thanks very much for all the hard work, and over to you.
Thanks very much, Russ, and for the great introduction as well. Yes, I will emphasize this has been a tremendous team effort over the years with a lot of different contributions from people in many fields. Okay, so as many of you know, I mean, the melting curve of iron is critical to understanding some of the most pressing questions about super Earths, be their internal structure or their thermal evolution. But stepping back, what are we looking for? If you look at the decadal surveys, we think about large questions like, are super Earths habitable? Is there life on other planets? And then we start sort of going down the list from there. And the primary one people think about is, are they in the habitable zone? Are they at the right distance for the irradiance from their star to have a surface temperature where liquid water is potentially present? But we also, we started this thinking about, what are the next steps? What are the next observational properties where we could start adding to the information about what makes a habitable planet? So on the Earth, we have a magnetosphere which protects the surface and the atmosphere from charged particles from the sun. So we wanted to go about asking, can super Earths have a dynamo generated magnetosphere? So that then takes you to the next level of the science questions, which is, can they have a solidifying outer core from the bottom up, which drives the strongest dynamos, and for how long could they be present? And so, of course, when you think about, can they have a solidifying iron outer core, you sort of ask, what is our information? What information do we have about iron at such extreme conditions? So this is a summary figure from Lars Sticksrud's 2014 paper on the melting of super Earths, where on the left axis, we have temperature in a log scale from 3,000 degrees up to 25,000 degrees. And on the bottom axis, we have pressure in megabar from 2 megabar or 200 GPa up to 40 megabar or 4,000 gigapascals. And so what you're looking at over the range of course, one Earth mass, the center of the Earth is at 365 GPa, and 10 Earth masses are up here at around 3,000 GPa. The only data point really on this plot at this time was shockwave work, up at there 250, 260 GPa. Everything else is calculations. And of course, calculations are getting better and better, but we'd really like some ground truth information on the melting curve of iron to best start addressing these questions. So back, as Russ mentioned, back in 2015, we proposed work at the National Condition Facility using the Discovery Science Program to determine the melting curve of iron at such extreme conditions. Okay, so how would you imagine doing this on a laser platform? You know, we all have pictures about how you can measure melting in a DAC or even in a gas gun. So at the NIF, you know, I'm going to show you a video of the thermodynamic trajectory we sort of take our samples through over the time scale of the experiment. So on the left is the temperature, again in log space, where the bottom here I think is 4,000 degrees up to around 25,000 degrees. And on the x-axis is the pressure in megabar from 1 megabar up to, again, around 40 megabar or 100 GPa up to 4,000 GPa. The black line is the Hugoniot. So this is the locus of states you can reach by the passage of a single shock. So if you shock the material, it takes you to a state along the Hugoniot. And this Hugoniot comes from Jerry Curley's iron equation of state. And then the red line is the melt curve, or the predicted melt curve from Lars Stickfruit's. Actually, I think this is also from Jerry Curley's equation of state. And so in these experiments, we use the lasers to drive a single shock into the sample. So what you're going to see is Lagrangian tracer particles following the path. So we drive a single shock, and then we allow that material to decompress. And then we put a ramp compression or a shockless compression wave back into the material, compressing it to high pressures and temperatures. And at the peak stress, we probe it with our X-ray source to evaluate the state of the material to test whether it has solidified. So I'll show that one more time. So again, we shock to a state in the Hugoniot, we allow the material to decompress, and then we recompress it relatively slowly to our peak pressure state, where we can then pulse with our X-ray diffraction source to say, is it solid? Has it solidified? Or is it liquid? Has it solidified? And to what phase has it solidified into? And so we can change the different states on the Hugoniot, mapping out where it solidifies at high pressure. And of course, as we talked about, this is a large collaboration between many teams here at Livermore, the University of Illinois, Carnegie, UCLA, UCD, Sandia, and the University of Rochester, LLE. Let's go one time. Okay, so in the state, you know, in the context of what does this mean for a planet? So what we really tried to do is we tried to take the iron in these samples through the same thermodynamic path that the iron would follow during the convective process in the liquid outer core. So now in the temperature versus depth within the core, you know, the iron is generally considered to be on an adiabat. So if you have some schematic adiabatic temperature profile here relative to your iron melting curve, at some point, you know, there are no more experimental data, so there's a rather large uncertainty in that slope or that melting curve. So these planets start out hot from the giant impacts, and over time they cool just by conduction across into the core mantle boundary. So as this planet cools, so how the core solidifies and the mode at which it solidifies will define how the dynamo forms and evolves. So one can imagine, you know, a very steep melting curve where the isentrope intersects that melting curve, and then you solidify from the bottom up, starting at the top, solidify from the bottom up like we do on the Earth. One could imagine a melting curve which is very parallel to the adiabat, and in that case, you would solidify through the entire planet very quickly, as you don't need to lose a lot of heat. Or one can even imagine a melting curve that is shallower than the slope of the isentrope, which would mean you would get solidification higher, sort of at greater or lower depths, so say at the core mantle boundary first, and then that would snow iron down into the center of core, which may inhibit convection or may just weaken the magnetosphere. So again, what we're really looking at is the slope of this isentrope relative to the melting curve. And so in my mind, that makes this, you know, the right space to look at this problem is in the pressure entropy plane. Okay, so let's just walk through what this means. So in entropy, and again, this is a simulated entropy field. So in entropy space on the left, where the units may not have as an intuitive feeling, but think of entropy as the amount of dissipation. So the red line is the Hugoniot, and the x-axis here is in pressure. Where again, we're at 100 GPa up to 1,000 GPa and 2,000 GPa. So with increasing pressure on the Hugoniot, you're increasing the entropy pretty dramatically. And so again, thinking about that same thermodynamic space, we shock to a state on the Hugoniot, say at 270 GPa or 300 GPa, and then we shocklessly compress it to high pressures. So we isentropically or quasi-isotropically compress it to high pressures. So now in this space, it's a horizontal line, and then we pulse it with X-ray diffraction. So we can evaluate at this given point in pressure entropy space if we've solidified the material or not. So that allows us to map out the melting curve, where of course entropy is an extensive variable. So you have a liquidus showing the boundary between pure liquid phase and the solid plus liquid phase, and you have a solidus at the boundary between the solid plus liquid phase and the solid phase. So again, in these experiments, what we're trying to do is map out the melting curve in the pressure entropy space so we can understand how cores solidify, thinking through back to this temperature depth space. So to do this, we have to use the National Ignition Facility, which is the world's most energetic laser. And of course, we're not using all the energy. We're not using 2 megajoules here, but we are using a pretty significant amount. So the NIF, if you've not seen it, it's an amazing place. You can take virtual tours. The building is huge. It's 250 meters, around 250 meters long, where the capacitor bays and everything is just tremendous. And I'll point out that the chamber is a 10-meter diameter chamber, sort of shown here at the end, with sort of the 192 beam paths kind of pointing into it. It's primarily driven to look for ignition. So we actually use an X-ray diffraction diagnostic called TARDIS, which is shown in a picture here. It's about the size of your hand. Oops, pardon me. It's about the size of your hand, and it's actually a little bit of it's designed to be in a watermelon shape so that it can fit between the alignment diagnostics at the NIF. But in this watermelon shaped, it's basically a watermelon shaped box that's shielded to protect X-rays, but inside are our image plates. So this is now a schematic shown at the bottom here is a schematic of the TARDIS diagnostic, where our sample package is basically put on the sort of front face of that diffraction diagnostic, which again is basically a shielded image plate box, where our sample is composed of a stack of samples. So again, the idea is we use the NIF laser. So we use 16 beams of the NIF laser to drive a shock wave, where we use beryllium as an ablator. It's a low Z, very efficient ablator, doesn't generate high energy X-rays. We then use germanium to shield the X-rays from our sample, our iron sample, and then a lithium fluoride window so that we can diagnose the pressure states while maintaining the peak pressure. That sample package is put on an X-ray pinhole to collimate the X-rays, where the X-rays are sourced by a plasma source. So we use another 24 beams of this laser to generate a plasma from either germanium or zirconium, depending upon the X-ray energy that we'd like. And then when we pulse that X-rays at our samples at peak pressure, we can then collect the diffracted X-ray beams from the image plates. And this is how we are able to distinguish and discriminate between phases. And I'd like to point out here that, even though our team is quite large, that team still does not represent the entire community of individuals that make this type of experiment possible. This experiment really utilized and really pushed the capabilities of the NIF laser and pole shaping capabilities. We had many hours working with the pole shaping teams. The teams that developed X-ray diffraction on a laser source at other lasers have really worked to evolve this. The teams that have developed the plasma X-ray sources, as well as and specifically the teams that developed the TARDIS diagnostic at the NIF, reducing the background has really helped make this experiment possible. Okay, so to go over that really in a bit more detail, NIF is a really amazing facility because it can give you such accurate pulse shaping. We want it to be better, but it does a really great job. And so we request a pulse shape that looks a little bit like this in blue, where this is laser power in terawatts for an individual beam. And these experiments, I apologize, this is not microseconds, this is nanoseconds. So these experiments last 30 billionths of a second, 30 nanoseconds long, where the pulse shape looks a little bit like this. So we have a sort of a flat foot that drives the shock. And then we have this gentle and increasing rise in intensity, which is what which correlates with the ablation pressure, and thus the gentle increase in pressure until we reach our peak pressure state, and then we can hold that pressure state and pulse it with diffraction. So again, this type of laser profile incident on the beryllium ablator transmits a compression wave through the beryllium, the germanium, the iron. And then the way that we diagnose those states is using a VISAR, a velocity interferometer system for any reflector, that measures the interface velocity between the lithium fluoride and the iron window. And because we know the equations of state, refractive index of LIF over such extreme conditions, as well as iron, our measurement of that interface velocity, where this is now velocity in kilometers per second and time in nanoseconds from 20 out to 36 nanoseconds. So we measure, again, we get a very steady shock wave. So this, shock wave is steady at the few percent level, which is, a sort of a testament to the capabilities of the NIF for pole shaping. And then we get this shockless compression wave and this nice long hold at the peak pressure state. And so then this shadowed region is shown where we're taking X-ray diffraction. So then the way we obtain the pressures is we perform a forward optimization and iterative forward analysis, which Suzanne Ollie's published sort of a technique on how to do this to obtain those peak pressure states. And this is showing a little bit about, I won't go through too much in detail, but if you have questions about the uncertainties, please let me know. So again, we do a hydrocode optimization to match the input pressure drive to the output interface velocity, which allows us to accurately constrain what the pressure history in our sample was. So by matching this hydrocode output, we can then obtain the histogram of pressure and density states at the time of the X-ray diffraction, where we have our X-ray sources on for about a nanosecond. And so we can obtain the time integrated pressure states during the time of our X-ray diffraction. And we actually get because of the pole shaping capabilities again, we get a very narrow pressure distribution. So we have a pretty small uncertainty in the pressure in the peak states. So getting to some of the raw data, I'll go through a couple of examples of the data points and the different types of phases that we see. So the first thing I'll say is, this is not diffraction from an XFEL. This is not diffraction from a synchrotron. This is diffraction from a plasma source. And so a plasma source at 550 GPa. So I'm pretty proud of this data. But if you are looking at this with the context of seeing synchrotron data or XFEL data all the time, pull it back a little bit. And so what you're looking at is a dewarping, a stereographic projection of the image plates. And what I'm showing here, I'm highlighting in yellow, is the region over which you'll see the data, the diffraction data from the iron. And so upon a experiment here we performed in 2016, we shocked to 230 GPa. So 230 GPa is on the mixed phase. So iron melts and starts melting on the Hugoniot at 220 GPa. It completes melting at around 260 GPa. So we shocked to 230 GPa into a mixed phase. You release to 120 GPa. That means now you're releasing now to a completely molten state. And then we ramped back up to 550 GPa, and then we pulsed it with X-ray diffraction. And so this, we expect, and so what we did observe was solidification into the HCP structure. So this is a bit textured, but you can see the HCP triplet in the raw data. And when we take a line out over the entire stereographic projection, what we've seen is in this region, you see the HCP triplet here, although it's not as refined in the line out, because what we've done is we've added, shown in the sort of the light pink here, we've added instrumental broadening. So we would expect to see this type of instrumental broadening for an HCP triplet. And if you even look at the data, you can actually track and see the C3 triplets, even though it's slightly textured. Okay, so then if you go up to, if you increase that entropy, you increase that shock strength on the first shock, now shocking to 260 GPa, which is just into a completely molten state, releasing to 140 GPa, and then ramping back up to 550 GPa, we observe partial solidification. So solidification, we observe with the diffraction pattern, a mixed phase state of both liquid and solid, which is In a qualitative sense, you see a bit of a halo around that same HCP triplet. And so when you do a line out, what we see, and this is shown for more in detail in this line out, is a fit of an HCP triplet and a Gaussian, which is we're representing as the liquid diffraction feature. And that is an excellent fit to this feature around sort of the 40 to 45 degree 2 theta angle. And so this was actually a really important experiment to observe this mixed phase, and I'll tell why a little bit later. And then as you increase the entropy even further, shock it to a higher pressure, shocking to 300 GPa, then releasing to 160, then ramping back up to 550 GPa, we observe no solidification. So we observe only this diffuse liquid scattering feature, sort of underlying this yellow highlight here, also shown in the line out here. We don't see any signatures for HCP or any other solid phase. So this again sort of provides that constraint in the pressure entropy plane on the melting curve. Okay, so I'm just checking my watch for time. So again, as I showed in those first two examples, we observe pressure-driven solidification in pure iron on the nanosecond timescale. That implies that there are a couple implications for that. One, that you'll solidify from the bottom up, and then also there's questions about whether or not homogeneous nucleation is the relevant model, and therefore, is the core nucleation paradox really a paradox? We also observe HCP as the equilibrium high pressure temperature crystal structure along the melt curve up to 10 megabar. And then, as I've shown, what I'll show here is that this is our final plot of the data in the pressure entropy plane. So this is entropy and pressure from 150 up to 1250 GPa. Again, the black line is the Hugoniot. The green points represent the pressure for incipient melting and pressure for complete melting. And then our data points where we measure liquid are shown in red, the mixed phase is in black, and HCP is shown in blue. So then what we did was we fit the melting curve, we fit both the liquidus and the solidus, assuming a constant entropy of melting, which is reasonable based on the statistics of melting. And we also force these, the liquidus and solidus, to go through the pressures of incipient complete melting. And so from this, we can obtain a fit to the high pressure. We can obtain the melting curve of iron in the pressure entropy plane from 250 up to 1000 GPa. And we actually have a pretty tight constraint on that. And then I also wanted to go through the justification for HCP. So beyond the fact that we see a triplet, some of it was textures. So you can say, well, what is the source of those spots? We can also look at this data in the context of what the equation state should be. If we tried to interpret, say, the strongest line as being from the BCC 110, or the two strongest lines as being from the FCC. If you try to interpret those diffraction signatures as being from BCC or FCC or any reasonable candidate, they're inconsistent with the equation state of iron, whereas HCP, interpreting that diffraction data as being HCP, is consistent with the equation state. So again, we find that HCP is a high pressure temperature crystal structure of pure iron near the melt curve up to 10 megabar. And then we have a pretty tight constraint in the melting curve in the pressure entropy plane, which is, I would say, the most relevant phase space for interpreting the thermal evolution of super Earths. And so again, but the next question is, can we take this to the pressure temperature planes where most people are sort of consistent and sort of thinking through it, and also the best comparison with calculations? So actually, from the pressure entropy plane, you can follow a two-step thermodynamic integration if you have some sort of second derivatives. And so what I'll show is that, so what I'll kind of walk you through is that in the, say, entropy plane, so this is now entropy as a function of density, but you can think of this as pressure too. You can start, say, take a point, I say take your reference point on the liquidus, which will be the pressure at complete melting, and say the temperature. And you follow a two-step thermodynamic path. You first isochorically heat that material to a higher entropy point, which requires the isochoric heat capacity to understand the increase in temperature. and then you isentropically compress that material to a higher pressure state along the liquidus, right? So these are the two steps. And the real question is, okay, what is the change in temperature as you follow these two steps? And that will then give you the melting curve and the pressure temperature plane. Okay, so to get the temperature increase by adding this delta S1 of entropy change, this is, the entropy is just CV over T dt, so it requires the heat capacity. Then the temperature change along an isentrope is one, you can look at the thermodynamic definition of gamma, which is gamma is d log T, d log V. So we know we need the isochoric heat capacity near our reference point, and then we also need the thermodynamic Granissen parameter over this range of density space. And we also need, I would say, the temperature reference point on the melt curve. So for that, we went to back to the Yu and Holmes data back in the 1990s for shock temperature measurements. And actually this data was sort of discounted because the lower pressure data, you know, in the solid phase and in within the mixed phase region didn't look reasonable. However, I would say that most shock temperature data in the solid phase or in the mixed phase region is difficult to understand because you're releasing through the mixed phase. You know, how do you understand the thermal diffusivities and the reflectivities? But once you get into the liquid phase, those are then again more easy to interpret. And so using the Yu and Holmes data, but only the data where you shocked above the pressure for complete melting, you can fit the heat capacity, you can fit the Hugoniot to obtain a heat capacity to those data points, and then you can also then extrapolate that data down to 260 GPa, which Nguyen and Holmes determined very accurately as the pressure for complete melting. So from this reinterpretation of the Yu and Holmes data, we obtain the melting curve, the temperature on the melting curve at 260 GPa is around 5,500 degrees, plus or minus around 700 or 600 degrees based upon the random and systematic errors, which we propagated in Monte Carlo, and also the isochoric heat capacity of 4.3 plus or minus about 1 kV per atom. So that data set was critical. And then also the Granissen parameter is really important over this pressure regime. So in the liquid iron, so the most accurate data on the Granissen parameter in liquid iron at ambient densities was from Anderson and Ahrens in 1994, and then also in the Nguyen and Holmes sound speed data along the Hugoniot in the same pressure regime. So then I fit an Altshuler form to this Granissen parameter as a function of density. And again, the density range we're talking, you know, so this is a extrapolation and a Monte Carlo error propagation across this data set. But the density range we're talking about in these experiments are really, you know, it's 12.5 grams per cc along the Hugoniot. It's around 14 grams per cc at 500 GPa and around 1800 or 18 grams per cc. So we're talking about sort of, we're really interested in sort of this regime of gamma, which is reasonably well constrained, even in extrapolation by the data. So using this technique, this two-step thermodynamic integration, we can obtain the melt curve from the reference point at 260 GPa along the Hugoniot up to 1000 GPa where our data tops off. And then we obtain, then we performed a assignment fit to the data and extrapolated that both up to higher pressures and to lower pressures. So I'd say the one nice thing this provides is, you know, the temperature reference for the Earth, the melting curve of pure iron at 330 GPa at the inner core boundary is now in an interpolative regime rather than extrapolating up from the measurements, the static high pressure measurements at lower pressure. And so we found that the temperature at 330 GPa pure iron is 6230 plus or minus 540 degrees. Then if you look to higher pressures where there actually is no data, you know, the highest pressure temperature measurements are by Simio very recently in 2021. And you know, so this is sort of the first data in this regime, sort of 3 times higher pressure than previous measurements, and it actually agrees really well with the Merard 2011 DFT calculations, and it extrapolates well down to the Anzolini et al. Melting curve measurements, where I would say where these temperature measurements have an uncertainty, you know, at low pressures of 500-600 degrees and at high pressures 1000 degrees or so. So one of the big questions that we got into when we actually started this campaign, and has actually driven a fair amount of research on the side of our experimental activities, was, these experiments last around 30 nanoseconds. So how are you dealing with the fact that the time, that these materials will take time to solidify? And so of course it's a question of magnitude. And so we actually worked with a large team of individuals, of experts we have here, at understanding the kinetics of phase transitions, the kinetics of solid-solid and liquid-solid phase transition, that led by John Beloff and Lauren Benedict and Philip Mient and Sebastian Hamill actually worked on this. And so what they did was they actually put together another equation state model that agrees reasonably well with our results. And they did some continuum detailed kinetic simulations of the solidification process. And one of the first things that they looked into was assuming homogeneous nucleation with reasonably calculated thermal diffusivities and surface energies. And they found that assuming homogeneous nucleation, you have to overdrive this a lot. And this is actually consistent with the idea of the core nucleation paradox, right? The core nucleation paradox says you have to overdrive and undercool the iron really significantly in order to nucleate a core. And as their simulations are consistent with that, assuming homogeneous nucleation. But I would say the problem with this is, we made one measurement where we saw a mixed phase. And what that means is that, in these experiments, it's a little bit subtle, but we shock into a liquid state, and then we compress it isentropically, and we saw a mixed phase. Now, if the physics was such that you had to overdrive it so far to observe solidification, you'd expect that once you started nucleating, you would nucleate into a completely solid state. Now, that's what the EOS suggests. So the fact that we observe a mixed phase regime either means that we're observing something close to equilibrium, or that growth into that completely solid state is limited by thermal diffusivity. But the fact that we also observe now complete solidification at lower pressures means we're not in a thermal diffusion limited regime. And actually, again, this mixed phase data tells us that we're observing near equilibrium solidification. And when we looked into that a bit more detail, the equations that are controlling the solidification timescale are extremely sensitive both to temperature and to the surface energy, where even though the fact this is 4 nines iron, there is a little bit of impurities in there which can dramatically lower the surface energy. So it's the fact that it's not 100% pure, and we're at pressures or temperatures of 6,000 to 10,000 degrees, which is giving us this capability to study equilibrium solidification. Okay, so using the melting curve, using our now recently obtained melting curve of iron to high pressures, what does this mean for the interiors of planets? Where of course we're acknowledging that we're looking at pure iron. So this will change depending upon the alloy of the planet you're interested in. But of course we have to start with pure iron because we don't want to go about and make measurements for every new alloy of any new planet that we're interested in. So we did some interior structure calculations to obtain the pressure at the function, the pressure at the center of the planet and the pressure at the core mantle boundary. So this is now pressure in log space versus planet mass from 1 to 10 Earth masses, sort of the super Earth regime. So for these pressures at the planet center and this core mantle boundary, we then relate those to the entropy along the liquidus so that we can say how much entropy do you need to lose to go from the planet, from solidifying at the planet center to solidifying at the core mantle boundary. Okay, so this is now the liquidus entropy along the planet center and the liquidus entropy along the core mantle boundary. And for each given planet size, this tells you the amount of entropy you have to lose to solidify that core, and thus the amount of heat you have to lose. So assuming a heat flux of 80 milliwatts per meter squared, which scales with the planet mass, this is from Lars Sticksrud's paper, we can calculate the time scale for solidification. Just a very simple model. And assuming sort of a 50% error bar, which is reasonable given the recent publications on the heat flux, the timescale for the solidification of Earth's core is around 6.2 plus or minus 3.4 billion years. And this, given that Earth's core is about 5% solidified, this supports estimates for a young Earth's core. And then as with the higher pressure data, what we actually find is that the solidification timescale has an interesting sort of shape to it. The solidification timescale increases pretty dramatically and reaches a maximum in the 4 to 6 Earth mass regime, and then starts to tail off as you go to higher and higher masses. So I think, the kind of the takeaway here is that super Earths in this 4 to 6 Earth mass regime could have a significantly longer dynamo, or significantly longer timescale to solidify a core, and thus a power source for a dynamo, and thus a magnetosphere. And so as Russ mentioned, these experiments were taken a while ago. It took us a while to write up the papers, but they were just published in Science just a couple of weeks ago on the measurements of the melting curve up to 1,000 GPa. Where again, I'll reiterate that we observed that pure iron is HCP at Earth core and super Earth core relevant conditions. We found that the kinetics of solidification are fast, which we believe primarily are due to the temperatures and the fact that, even though they're 4.9s, they're still not high purity. And this can imply, and I would say this, one way to interpret this is that there's little evidence for core nucleation paradox. Given how we can take the iron from the pressure entropy state to the pressure temperature plane using experimentally constrained derivatives, we find the melting temperature at Earth's inner core boundary of 6230 plus or minus 540 degrees, which is no longer a extrapolated measurement, but is an interpolation regime. Given that we observe pressure-driven solidification over the range of states of our experiment pressures, we find that super Earths will solidify from the bottom up, which enhances their ability. It doesn't necessarily, top-down solidification doesn't stop dynamos, but it's found that super Earths bottom-up solidification powers them the best. And that the greatest longevity of magnetospheres on super Earths, or the greatest longevity of power source to drive a dynamo, occurs in the 4 to 6 Earth mass regime. And I would say that, this has been an incredibly fun project. And one of the things that's been teaching us a lot is that, dynamic compression really does have its benefits, especially when coupled to light sources. It sort of offers you a unique opportunity to make detailed measurements about the melting curve at some of the most extreme conditions of interest, both to the Earth and the planets, extrasolar planets as well. And actually, I'm really most excited about sort of the new efforts in coupling new dynamic drivers to light sources going on at the APS and LCLS right now. So if there's any questions, I'd be happy to take them.
Thanks, Rick. That was beautifully presented. I'm sure there are questions and comments. Please just unmute yourself, raise your hand, or put a question in chat. So Burkhard, go ahead.
Hi, Rick Kraus, this is amazing. We're cheer you on, and maybe Felipe has the same question I have. I sort of wonder, you have the subjective background when you analyze. I'm wondering if you can really identify, or how certain you are when you say you're completely solidified, that there isn't some small liquid fraction lurking somewhere. How sure can you be? So I imagine the background subtraction is not true.
Yeah, thank you, Burkhard. That is an important aspect, and one that we've labored over a tremendous amount. And I would say that this is, Amy Yannay and John Eggert have spent a tremendous amount of time looking at this. And actually, for the specific question of how sure you can be, the background subtraction algorithms, there's a couple of different ways to do it, and we looked at a couple of different ways. And the background subtraction algorithms are most likely to, take away the liquid structure. So we can be fairly certain I would say, and we looked at, the signal to noise, fairly certain at the 5 to 10% level that there is no solid fraction.
So let me ask, are you consistent with the equation of state then? Because there is some materials you travel along this mixed region for a large pressure range.
Yep.
And I look at your data, I'm not convinced it's compatible with the theorists are saying. I'm sure you checked this, right?
No, actually, I would say it is consistent. Let me just walk through that.
That'd be good. Thank you.
For example, so I showed in the pressure. So let's go back to the very what you're talking about. What Burkhart's referring to is the fact that, you know, if you follow an isentrope through a melt curve, so this is now following the trajectory of the material, this material gets stuck on the phase boundary and is buffered by the phase boundary. It's in a mixed phase until it gets off that phase boundary. So that's actually consistent with our interpretation of this data, in that there is, say, at constant entropy, so along this melt curve, you would be stuck on the phase boundary for a large pressure range, even larger than I would say that EOS would suggest. So again, now following a horizontal line, say from this pressure point at 260 GPa, you would release and you'd get back on that mixed phase almost, you'd get back on that mixed phase almost immediately, and you wouldn't exit it till around 1000 GPa. So our data is consistent with, is thermodynamically consistent with that picture.
Okay, very good. Thank you.
Okay, Philippe, do you have a question?
Yes, I do. Thank you. Hey, Rick, this is Felipe Gonzalez from Berkeley. This is great work. Congratulations. I read your paper with great interest, and I have two questions. So the first one is related to the crystallization of the core. And as I understood, you assume certain heat core mantle boundary heat flux and derive the solidification time.
Yep.
But I did not understand the relationship with any interior profile, like a thermal profile for the interior. For example, what happens if a model suggests that the temperature at the very center of the planet is 5000 Kelvin and another model suggests it is 20,000 Kelvin? How is that this does not depend on the initial temperature that you start crystallizing from?
Actually, that's a really good point. So what it absolutely will. Let me find a reasonable. Actually, let me go back to the data. So what we are calculating is the time scale from starting to crystallize to completing crystallization. So the time it takes to go from starting crystallization at the center to completing crystallization at the core mantle boundary. That has nothing, that doesn't say anything about the fact that, well, maybe giant impacts, and of course that assumes that you're starting in a completely liquid state. But of course, there's been giant impact calculations, and we've mined those giant impact calculations to show that, yes, you would definitely, you know, in a statistical space, you would expect that the cores will be completely liquid. But it doesn't say anything about how long it takes to get from, say, 15,000 degrees down to the melting curve at 10,000 degrees or 25,000 degrees down to the melting curve at 10,000 degrees. You know, there's still that unknown amount of time to remove the heat to go from, say, the initial thermal state to the melting curve.
See, that clarifies it. Thank you very much. And the last question, if I may, regarding the methodology, I understand that there's, from the Hugoniot, an isentropic decompression followed by a perfect isentropic ramp compression, right? So what happens if this ramp compression is not perfectly isentropic, it is steeper than isentrope? Would that result in higher melting temperatures?
No, so actually we did account for that. And so I am not presenting I am presenting the final entropies. I am not presenting the entropies on the shock state because I accounted for heating due to the X-ray ablation plasma and heating due to the concurrent heating of X-ray light source. So there are two excess sources of entropy I've accounted for, and I've systematically added those corrections into the entropy states. So you're also referring to the fact that shockless compression, so a shock will add entropy, but shockless compression also adds entropy because in a solid, there's plastic work heating done by the strength, deviatoric stresses of the material, and in a liquid, there's viscosity. However, for most, I would say all but one of these experiments, the most of the compression was done in the liquid state. And for the viscosity of our assumed viscosity and calculated viscosities of liquid iron, the amount of heating done in sort of in the temperature space is a few to tens of degrees. Now it's not a significant amount of work done, and actually would be negligible relative to the size of these error bars. But it is an important thing to consider, and we did include it, and we did consider those, and that's actually presented in the supplement too. And I'm happy to talk about that in more detail.
I see. Thank you very much, Rick.
Okay, thanks. Stephen, and then Urshan and Maggie. Stephen?
Hi, nice to meet you, Rick. I'm Steve Burns at the University of Rochester.
Hi, Steve.
I had a couple of questions, one of which is that when you're in your HCP phase, the material is a solid. But a lot of your modeling seems to me to be done on the basis of liquids. Okay, for example, I might ask, what is the role of shear stress in the HCP phase? I know you attributed that to the irreversible damage that you got, and it causes heating in your sample. But is there any other way that the shear stress might be coupled in to the laser pulse as it comes through on the Hugoniot, and to the description of the pressures or stresses maybe that would be present in that system? Okay, that's number one. And number two, when you talk about the entropy, it seems to me that you generally keep it as a function of temperature. But of course, pressure is an independent variable, and the entropy would always be a function also of the pressure with the temperature held constant. And is that built into your models? Maybe I missed it. I probably did. Okay, I'll just leave it at that.
Okay, no, thanks, Steve. Okay, so two questions there. I think there are two aspects to thinking about the shear stress. One, which we talked about with answering Philippe's question, which is, does the shear stress create any work which increases the entropy that we are not considering? And so again, if you look at, looking at the data for all but this lowest entropy point, which there is a significant amount of compression in the solid phase, but even using the models, the amount of entropy generated is still sort of within the error bars here. Every other point, the amount of plastic work heating due to shear stresses would not, would very negligibly increase the entropy. And so that's why we did not include it in our additional entropy in these points. The other one was a question about the stress state. So to obtain the stresses, we did a forward optimization to the iron, to the interface velocity between the iron and the lithium fluoride, where we used hydrostatic equations of state from lithium fluoride and iron. These hydrostatic equations of state were benchmarked against NIF ramp compression data obtained by Ray Smith. And so I would say this is a point where the expected shear stress may affect the peak pressure state at the level of a few to tens of GPa, maybe probably a few GPa, maybe up to 10 GPa, which is still sort of within the systematic error bars here.
Not very significant.
And not very significant. So then your second point about, let me get back to how we interpreted, I apologize, I don't remember exactly. Right, so your point is that entropy is, well, it's going to vary as a function of temperatures. It's really depending upon what you want to hold constant. And so in this case, we made sure to be self-consistent in how we are approaching that. So again, the thermodynamic paths I'm considering are one in which I start at a reference point on the solidus, which has some initial entropy, some initial pressure, some initial density, and some initial temperature. And then I add entropy isochorically to a state that is now a new entropy, same density, isochoric compression, new temperature, and this again will also be a new pressure. Right, so I'm accounting for the fact that the pressure will change, and then I go from that density entropy point to the density entropy point on the liquidus at high pressure, P2, which we care about most. So I am including the fact that the pressures will change, and I'm just tracking that based upon which second derivatives, which heat capacity and gamma, because the heat capacity, the isochoric heat capacity, which is easy to get from the slope of the Hugoniot, can only be used to get this. I wouldn't use an isobaric heat capacity because the Hugoniot, the derivation of the Hugoniot is not as easy to get the isobaric heat capacity. Does that make sense?
Thank you. Thank you.
Okay.
Okay, thanks very much. Urshan, you have a question?
Yeah, I do actually. Thank you, Rick, for this beautiful presentation. Even I could follow most of the things. One of your slides, you had shown the breakdown of the X-ray diffraction peak between liquid and the solid. I think previous. Yes,
Yep.
this one. My question is related to that insert. I don't see the statistics on it, which says arbitrary units, and I don't know what the count rates are, what is the background, and how interrelated are the peak positions, peak intensities, and peak line widths.
So I wish Amy was on the call to address that question. I would say here I would say we did not try to include all that quantitative information for the purpose of we are not trying to quantify the signal from the liquid or the signal from the solid. And the real test we were trying to make was, is there any way that we could fit this pattern with just a solid or just a liquid? And the answer to that is no. And so maybe we didn't sort of present that as as that specific hypothesis test. But I think we did not want to take it as. Go ahead.
It's one of your critical data that comes from the resolution of this peaks, right?
Yes. Well, it's the critical data to test whether or not there is solid and liquid there.
Right. Right. Okay. Thank you.
Yeah, that's right. Okay, Maggie, would you like to ask your question?
Oh, sure. I was just wondering about what kind of difference the fit to the Gruneisen parameter makes. And if you intentionally chose not to fit to the Brown-McQueen sound speed data, or like why you chose liquid versus solid or Hugoniot versus isentrope for the Gruneisen.
Okay, let me get to that. All right, so the Brown and McQueen data, at least at in the same pressure range, is pretty consistent with Nguyen and Holmes, except for the Brown and McQueen data. This is the data which is on an alloy. Forgetting the top of my head. I remember looking, I remember that being pretty consistent, although the Nguyen and Holmes data had smaller error bars. So I chose to fit to the smaller error bar data. I chose not to use the isentropic sound velocity data because it is expected that you have a slight change in gamma as you go from the solid to the liquid phase, and there is some slight temperature dependence. So I chose to use data that was as close to the same temperature or entropy as the experimental use. I did fit with different forms. I tested the sensitivity to different forms of a Gruneisen fit. I tested, just the power law form and the Altshuler form. I forget which other ones I tested. But again, it's not too sensitive because we're not looking over that large of a range of density space.
Perfect, thank you.
Yep.
Okay, Xue Zhang had a comment and question. First of all, thank you for the excellent work. Could you clarify whether the HCP structure you used for fitting the X-ray diffraction data is based on low temperature crystals or high temperature simulations? Structures of solid iron are complex at high temperatures, for example, BCC and HCP could both become close packed. I'm not sure about the latter because BCC is not close packed, but go ahead, Rick.
So with this, we were actually, we did not assume a C over A ratio. We were able to obtain a C over A ratio that was consistent with high temperature iron. Does that answer the question?
Sorry, maybe I can try to clarify a little bit. So basically, it's not quite clear to me that whether the HCP structure that you used for doing the fit is based on, say, first principle simulations, or it's based on, say, experience, or for the relatively lower pressure equation state data, or XRD data. Because if you use first principle simulations, the structures that you see at such high temperature would really be complex. And if you look at the coordination number, BCC and HCP are both close packed, really close packed. It's not 8, for example, for BCC.
Maybe I'm confused by your question, because the solid diffraction patterns are very distinct between BCC and HCP. And from the triplet, we obtain the lattice parameters and the C over A ratio. And that's how we're able to distinguish between both from the lattice parameters and the EOS fits, and also from the fact that there's a triplet. That
right, I agree they are distinct at low temperatures, but I was just wondering if they are still that distinct at high temperatures.
I guess I'm not following the question. Our experiments are at high temperatures, and so go ahead, Russ.
Yeah, I was just going to say, I mean, these are just simple fits. Okay, so it's independent of any kind of simulation. Now, you can't rule out that there's some derivative HCP structure, maybe a mixed packing or some polytype, but the basic HCP form fits the data. It's almost an Occam's razor argument based on the triplet.
Well, we can discuss it later, but I think because the complexity of the structure, whether the fit, whether BCC can be fully excluded by this comparison, it's not 100% clear to me.
You're saying that BCC will have more than one line in this. You're saying that BCC could have a triplet in this.
That's what I'm suspecting. That's also why I'm trying to ask.
Perhaps you could go back to your slide that shows the equation of state, assuming the 3 different structures.
Yeah, exactly. So again, we looked at all this data and tried to interpret the data as BCC, and you'd get a density that would not agree.
Yeah, I understand. I read the paper. I'm just still having that question.
Shuai, so this is Ryan. I think if you have a triplet, you wouldn't consider the structure BCC anymore. Could you clarify what you mean by BCC is close packed? Because I don't think of that as close packed.
Yeah, hi, Ryan. That's in terms of the coordination number, because from simulations, it's been shown, in published ones as well as ours. If you look at the coordination number, it's close packed. BCC, the coordination number is not 8 at a high temperature. It's something like 13.
But then it's not BCC, is it?
No, it's not BCC.
It's high temperature BCC.
Well, but BCC has no interpretation of it. Anyway, it doesn't depend on the temperature. It's just the arrangement of atoms.
Yeah. So that's why at high temperature the structures are really complex. It still have some differences in around the first value if you look at the pair correlation function. But from that, if you calculate the coordination number, it's close packed.
But let me jump in here. I think the burden is on you, that you say with your high temperature simulation that this is compatible with Rick's experiment. Based on all we know so far, it is not. And I'm happy to cheer you on and see, maybe it is compatible. It's not obvious why that should be. So X-ray diffraction probe long range order over tens of thousands of atoms. So while the coordination number is probing something else, and you can argue whether there's a collapse of the first and second shell in DCC, but it's not directly related to what Rip's measuring. That's my 2 cents. But we cheer you on. Please do more work.
Yeah. So, yeah, thanks for the comments, Farkad. Yeah, you know, our project is not finished yet, so I don't have a very clear answer. So that's why I still want to ask here. You know, but anyway, I really like the work. I think it's great, Rick.
Great,
Okay, thank you very much. Okay, Tyler, you have a question?
Yeah, thank you. Great talk. First, a quick clarifying question. If I remember correctly, you said that your understanding of the mixed phase kinetics is determined, or at least partially determined, by the thermal diffusivity at those conditions. Is that correct?
I said one could imagine a scenario where just looking at that mixed phase state, it could be dramatically overdriven, but the thermal diffusivity, the ability to flux heat away from those crystallites, is actually slowing its ability to get to complete solidification, right? So if the thermal diffusivity is really, really, really low, then you could misinterpret that mixed phase state as being in equilibrium when actually it should be, you know, interpreted as being far from equilibrium.
Okay.
However, what I'm saying is the fact that there are at slightly lower entropy states, which you wouldn't expect the thermal diffusivity to jump up dramatically, we observe complete solidification, and therefore we don't believe we're limited by thermal diffusion and the ability to heat flux away, or the flux heat away from those crystallites.
Okay, great. Yeah, I was just going to ask how that might compare to the, I know there's not diffusivity measured in exactly these conditions, but I know that there's still kind of a lot of research in that area on low conductivity and diffusivity, but it sounds like it doesn't, it's an unrealistic value is what it sounds like, and it doesn't even matter because you have other evidence for it.
It's an unrealistic value, and the values we use were actually calculated for this project from Mike Desjardins. So he has ways of calculating that from his DFT.
Okay, great, thank you.
Yeah, of course.
Okay, thank you very much. Are there any more questions? Great discussion. If not, join me in thanking Rick for a great presentation. Congratulations on the work. And we'll see you all next time.
Thank you, Russ. Thanks so much, everyone.